whenever we enter a vertex, there should be an edge leading out of that vertex, right? Otherwise, we get trapped at that vertex. So for an Eulerian cycle to exist in a directed graph, uh, clearly every vertex other than the source should have in degree equal to out degree, because for every edge that we consume when entering that vertex, there should be another uh, edge that has not yet been consumed that we could exit from. And for the source also, if we exit the source the first time, finally we want to enter back into the source. That's where we want the cycle to terminate. And so even for the source, the in degree and the out degree should be equal. And there could be cycles, Eulerian cycles, where we uh, visit the source multiple times during that cycle. But still, the overall in degree needs to be equal to the overall out degree. And if we want a directed graph to have an Eulerian path, which is not necessarily a cycle, then either every vertex should have in degree equal to out degree, in which case we'll have an Eulerian cycle, or if we want an Eulerian path that starts at a particular vertex S and ends at a particular vertex D, then clearly for every other vertex in that graph, whenever we enter that vertex, there has to be a fresh edge that we can use to exit that vertex. That means every vertex other than the source and the destination should have in degree equal to out degree. The source itself is allowed to have uh, an out degree that is one more than its in degree, because uh, we assuming that we don't come back ever to the source, that exit, the very first time we exit the source, that event is not going to be paired up with another event where we enter back into that source necessarily. It's possible we could come back to the source even along that Eulerian path, but then we'll leave it again, because finally the path ends at a different vertex, which is the destination. And likewise, by the same argument, for the destination, the event where we finally enter into it is an event that has no counterpart, in that we don't ever exit that destination. So the in degree for the destination is allowed to be one more than the out degree, right? So this vertex, which has an out degree that is one more than its in degree, will be the source of the Eulerian path, and this will be the destination of the Eulerian path. And I went through the proof of this in the foundation videos. For undirected graphs, the proofs for directed graphs would basically be exactly the same argument. Uh, but interestingly, that proof used a way of constructing the Eulerian path, which is actually the way that we will have to code up to solve this problem. I didn't realize it when I made those videos, but I was delighted that the algorithm itself is not new. It's just that we need to implement it properly. Okay, so Dheeraj asked, what's the difference between graph traversal, depth first search, breadth first search versus Euler cycle? So one thing that you can notice immediately, and Shiva mentioned DFS. Let's note that when we are talking about Eulerian cycles, even in this simplest example here, you can see that you're along an Eulerian cycle, the same vertex can be visited multiple times. Like JFK, you start out from JFK, uh, you come back to it, it appears a second time, and then it appears a third time. Whereas when you look at depth first search, and the fact that depth first search really constructs a tree, each vertex is visited only once, right? We don't come back to that vertex again multiple times in a regular depth first search or in a regular breadth first search. So the fact that the same vertex can appear many times along an Eulerian path means that we can't just blindly use depth first search. At least not the kind of depth first search that uh, we are familiar with for graphs as well as for trees. So that is, I would say, a primary difference because of which we can't directly appeal to the depth first search template in order to solve this problem. We'll have to do something more. So in general, if there is a problem which requires the traversal of all edges, we should think Eulerian graph. Yes, if we want to traverse all the edges in a graph exactly once, that is an Eulerian graph. Can you please summarize again the Eulerian cycle rule on directed versus non-directed? Uh, well, let me show the slide again. I don't want to spend too much time on this because we we need to get through the implementation, which is going to take some time. Uh, we are going to assume by default that whether it's a directed graph or an undirected graph, the graph has to be in one piece. You can't have uh, you can't have this kind of scenario, right? So let's assume that it's connected if it's an undirected graph, and if it's a directed graph, at least ignoring the edge directions, it's connected. But that's not sufficient. In an undirected graph, for there to be an Eulerian cycle, every vertex should have an even degree. And for there to be an Eulerian path, either every vertex should have an even degree or there should be exactly two vertices with an odd degree. And those two vertices are going to be the source and the destination for the Eulerian path. In an undirected graph, you could pick either of them as the source and the other would become the destination. In a directed graph, again, the graph should be in one piece when edge directions are ignored. And for there to be an Eulerian cycle, the in degree must equal the out degree for all vertices in the graph. For there to be an Eulerian path, which is not necessarily a cycle, either all vertices should have in degree equal to out degree, or there can be at most two vertices which don't satisfy this condition. The source of the Eulerian path will have an out degree that's one more than the in degree. The destination of the Eulerian path will have an in degree that's one more than the out degree. Shobit?
Yeah, hi Omkar. I just wanted to quickly check with your statement when you said that in DFS a vertex is visited only once. So
Hmm.
you mean to say the bottom protrusion, or like I thought that when we do a DFS there are left protrusion, bottom, and the right one.
So you're talking about trees, right? So with
Exactly.
trees, there are no cycles. So obviously, when there are no cycles, you visit every uh, by visiting every edge exactly once. You're visiting every vertex also exactly once. I mean, you don't arrive at that same vertex multiple times along different paths,
Okay.
right?
Okay.
Whereas in a graph, you should compare this. You should think about the depth first search on graphs, because here we're talking about graphs which can have cycles, and when you have cycles in regular depth first search, you see that there is a back edge going back to an earlier vertex, and you just ignore it, right? You don't again go to that vertex and start uh, finding ways to exit that vertex, right? You
Okay,
don't.
but even with the DFS tree, when we backtrack from the recursion, we can like in the background we can see that there will be one left and one bottom and one right, right? So I just wanted to clarify that statement. So even with the when we are building DFS tree,
Hmm,
when we backtrack from the recursion, we
hmm.
can say, okay, this one would be the right one, and like
Yeah, but when you backtrack, uh, you are recording the fact that you are in the middle of the adjacency list, right? You just temporarily went down some path. Now you've come back. You are proceeding on from that adjacency list. Uh, you are marking it. I mean, it's still there's only one place in the stack where the vertex appears, right? If you look at the call stack for the depth first search tree, you never have the same vertex appearing multiple times in the call stack.
that can be said for the tree as well then.
Yeah, yeah, it's there for tree as well, but trees are a very you know, they're a very simple example, whereas here we are talking about graphs.
Okay.
Uh, so yeah, it's different from depth first search for on trees and on graphs,
Okay.
because here, if we want to build an Eulerian path by, you know, doing something like depth first search, we're going to have the same vertex appear multiple times in the stack.
Yeah, yeah, I get that point. Yeah. Okay. Fine. Thank you.
Can we apply topological sort? Divya, topological sort applies only if the graph is acyclic, since there is no, since there can be lots of cycles. In fact, uh, most Eulerian, of course, for Eulerian paths, it's not necessary for there to be a cycle, but even in these simple examples they gave, like example 2 had cycles. So we don't use topological sort when there are cycles. Uh, I always, and plus, we are talking about Eulerian paths here, so we need a different algorithm to uh, construct these. It's not clear how topological sort would lead us to uh, that kind of uh, construction where, you have to come back to the same vertex multiple times, which is not what it's for. The whole idea behind topological sort is that you can proceed in a linear order from left to right without ever visiting a vertex again. I always had this question after watching foundation video, that why don't we use degree to find a cycle in any graph? Uh, Degree to find the cycle. Well, the degree wouldn't really, like, if a vertex has a degree of 5, how does it, this could be a vertex with degree 5, right? There may or may not be a cycle. I'm not sure how degrees themselves would convey that information. Um, but the fact that, uh, if you have n vertices in the graph, there can be at most n minus 1 edges that you can add without creating a cycle, right, to connect them all together. So I'm talking about an undirected graph. So as soon as you have more than n minus 1 edges, uh, which is exactly the number of edges that a tree has with n vertices, you will definitely get a cycle. For directed graphs, those cycles are more complex because we do need to keep track of back edges. So some of the degrees. So the point is that there could be cycles in the graph, but there may not be Eulerian cycles or Eulerian paths in that graph. Right? It's possible for a graph to have a cycle but not have um, an Eulerian path. So let's just create a simple graph. This graph has a cycle, but I could create a graph like this. There is no Eulerian path in this graph. So looking at the degrees themselves won't provide us that information. In degree is equal to out degree also. Uh, yeah, so that is something we can do. That is the condition for there to be an Eulerian cycle, assuming that the graph is in one piece. So if I give you a graph which has which is in two pieces like this, the in degree is equal to the out degree, but there is no Eulerian cycle in this graph because the graph isn't in one piece. It's completely disconnected. So since we have done strongly connected components, obviously if there is an Eulerian cycle in the graph, all the vertices in that graph has to have to be part of the same strongly connected component. So that has to be, so they all have to belong to the same strongly connected component. But not necessary for there to be an Eulerian cycle. Of course, for Eulerian paths, they don't have to be, because you can have an Eulerian path which goes like this, right? It could start here and then go like this and then end somewhere else. So this graph is not, uh, you can't see, this graph has two strongly connected components. This is one of them and this is the other, right? So there can be multiple strongly connected components um, for an Eulerian path to exist. Anyway, so it's more complex. That's the bottom line. It's not just a matter of counting in degrees and out degrees. If you DFS from every one, it should count all nodes, all counts the same. Uh, anyway, so let me actually move on, because I'm sure with how many people are here? 78 people. I'm sure there might be lots of different suggestions in your mind, but since we have only uh, 2 hours, we've already passed 30 minutes. I'm just going to let me explain my thought process, and then we can come back and see if you have any other thoughts. So with this analysis should be good enough. I'm going to um, describe two different algorithms for constructing Eulerian paths, one of which I already explained in the foundation videos, but let me present it in the context of our problem solving strategies. So the first algorithm uses a decrease and conquer approach. So what is a decrease and conquer approach? It's an approach where we just look at the leftmost or the rightmost piece of the input and try to do the bare minimum work needed for it, and then imagine that somebody else is going to be uh, doing the rest of the work. So since we need to construct an Eulerian path which starts at JFK, our Eulerian path is going to be looking like this, right? It'll have a bunch of airports and then finally ending up at some airport. So what um we could do if you want to use a decrease and conquer approach is to do the bare minimum work to infer what this first ticket should be. Right? What should be the first ticket out of JFK, or let's call it the source. We're given the source of the Eulerian path. Uh, what should be the first edge we exit from in order to uh, build this Eulerian path? And let me actually take the example of an undirected graph, as that would make it uh, uh, easier to analyze. So we need to figure out what these vertices are in sequence to build the Eulerian path. But then we have these edges, right? I don't want to draw directions on them, but these yellow things are the edges. So let's try to figure out what the first edge should be. Now, suppose S has um, multiple edges out of it. Let's say, for argument's sake, that it has 4 edges out of it. And these 4 edges go to 4 vertices. Question is, which edge should I pick? So it looks like I have a choice. Uh, the problem is that what if I go down an edge and I find that I can't come back. Right? Suppose I pick this edge, I use up this edge, and this is one particular region. And by using up this edge, I'm able to, let's say, explore all the vertices here, but I can't come back. That means I can't visit the other three edges, right? And so, what would you call this kind of edge along which we can use it? Obviously, each edge has to be used exactly once, but then we can't come back uh, uh, to S and to the other vertices that are reachable from S in the other directions. Um, some of you might not have attended my earlier advanced graphs classes, but now, uh, so this may or may not make total sense to you, but this kind of edge is called a bridge. A bridge is an edge whose removal disconnects the graph. I just want to emphasize we're talking about undirected graphs here, although similar analysis could be done for directed graphs, which would be a little more complicated. But the idea of a bridge, which is defined for connected undirected graphs, is that it's an edge whose removal disconnects the graph. So we have to use up all the edges, right? So that means we have to use a bridge edge as well. But the bridge edge should be the last edge we go along, we use, because if we use it the first time, then we won't be able to come back because its removal is going to disconnect this part of the graph from the rest of the graph. That's what it means for this edge to be a bridge, right? So let's say uh, I avoid a bridge. Let's look at a non-bridge edge. What is a non-bridge edge? A non-bridge edge is an edge whose removal will not disconnect the graph. That means if I consume this edge and I reach here, as far as I am concerned, the graph is still connected, right? There is a path going back to S, right? Let's actually differentiate between the two problems. Suppose we look at the Eulerian cycle problem. We want to construct an Eulerian cycle. We know that every vertex in the graph, in the connected undirected graph, has an even degree, and we want to construct an Eulerian cycle. So we pick any vertex to start from. Let's say we pick vertex S, and we followed an edge which is not a bridge to vertex V. We know that the Eulerian cycle will end back at S. And because this is a non-bridge edge, once we reach V, what is our remaining task? Right? We picked a non-bridge edge and we reached V. Now what is the problem reduced to? Now the problem is, it's as if, so since I've used this edge, I'll pretend it's not there. The problem is now to construct an Eulerian path from V to S. Does that make sense? We have to find a path from V that visits every edge of the graph and ends at S. And since every vertex had an even degree to start out with, uh, when I consume this edge, this non-bridge edge, and I remove it, what happens to the degree? Well, the degree of every other vertex remains the same. The degree of V reduces by 1, the degree of S reduces by 1, and if both of them had an even degree to start out with, they will both have an odd degree now. Which means that there is still an Eulerian path since there are exactly two vertices with an odd degree, and so I can, in principle, start from V and follow an Eulerian path ending at S. Now, how do I do that? I give that problem to someone else. I just figured out what the first edge is, and that's it. That's all I want to do. Now, let's say I hand the problem to you. Now, you analyze the edges that are remaining that are incident on V. So maybe there are, I don't know, 4 edges again incident on V which have not been used yet. You can pick a non-bridge edge again to uh, to consume from V. So If you use a non-bridge edge, that means wherever you end up with, let's say you ended up at U by using this non-bridge edge, you pretend that this edge is gone since you've consumed it, and because it was a non-bridge edge, uh, there is the graph is still connected, right? Even though I'm not showing it that way here, the graph is still connected, and the remaining degree, right? The edges that are incident on the vertices which are not yet been consumed. Just pretend that we are deleting the edges that we are walking along. So in the remaining graph, uh, we will again have we will again have an even degree because we had first deleted the first edge from S to V, so that made V have an odd degree. Now that we exited from V, it again has an even degree, but U will now have an odd degree, and S also has continues to have an odd degree, and so that means we have a graph where which is connected, right? Since we have only followed non-bridge edges, and which has exactly two vertices with an odd degree, U and S. So there must exist an Eulerian path from U to S. And so I give that remaining problem to someone else to solve, right? So the first two managers just pick the first two edges, and the remaining problem is now shrinking in size by one edge each time. You see that? Now there might come a point where there is a there is a vertex, let's say X, we reach, and maybe the only edge out of it is a bridge edge. In that case, we have no choice. There is no non-bridge edge out of X, so we just follow the bridge edge. And the claim is that this would be the only edge out of X. And if we are forced to follow a bridge edge, must be the case that this is the only edge that is incident on X now. And it's okay to follow a bridge edge when it's the only edge left, because by using it, we, we completely uh, have consumed the vertex X. We never have to come back to it. So it's okay to consume it in a way that uh, we never return to X or anything on the side of X, right? Uh, so obviously the problem is if there are two bridge edges out of X, right? If there are two bridge edges out of X, what does that mean? It means that if we follow one of them, we will not be able to get to the other. By the way, I'm showing them with arrows, but I should really have undirected versions here. And so the claim is that this kind of graph will actually not have an Eulerian uh, path, right? Because we are at X and we have to make this choice between two bridge edges, then you know it's impossible because following a bridge will burn the bridge, right? We consume the edge. So whenever we burn a bridge, we have to make sure that we are never going to return there, right? It's true in real life, but also here. We burn the bridges only at the very end. As far as possible, we only consume edges which are non-bridges. Uh, that is what allows us to use a decrease and conquer uh, approach in a way that the problem size shrinks by one edge each time, right? And you can see here that the Eulerian cycle and the Eulerian path problem are to be seen together because maybe the original problem was an Eulerian cycle problem, but that's just an Eulerian path problem that starts from S and ends at S. And obviously, in the next step, once we figured out what the first edge is, the remaining problem is going to be a problem of the problem of finding an Eulerian path from one vertex to some other vertex. So the algorithm here is simple in the sense simple to to write down, obviously not simple to design. Repeat the following until all edges are consumed. right? So if you are at um, wherever you are, wherever you currently are, um, follow a non-bridge edge out of that vertex. Actually, this is going to be step two, you can say. Step one is identify which um, which incident edges are bridges. Right? I should probably rewrite this. Repeat the following until all edges are consumed. So basically, if you are at vertex X, identify which edges incident on X are non-bridges, right? Or bridges. You can say obviously if you know what the bridges, which edges are the bridges, you know what which the non-bridges bridge edges are, and pick any non-bridge edge to leave X. Okay, so basically, if the starting vertex uh, is the source S, right? So let's say the current vertex starts out being the source. That's where you start out with. Um, so I'm going to call the current vertex as X. So X starts out being the source, and then identify which edges incident on X are non-bridges. Pick any non-bridge edge. Suppose we picked the edge between X and Y to leave X. Now you're at Y, right? So basically, your current vertex is going to become Y, right? And then you go back, you keep doing the same thing. Which edges incident on that vertex are non-bridges, and pick any non-bridge edge to leave X, right? And if there is only one bridge edge left, in brackets no non-bridges, then burn the bridge, right? Consume the bridge. Does that make sense? This is what we are intuitively doing. I'm not going to like code up this algorithm, because for the simple reason that um, identifying which edges are bridges and which are non-bridges, this is something we've done in an earlier advanced graphs class. This we know takes order m plus n time, right? Assuming we use Tarjan's algorithm, right? An advanced DFS application. Those of you who haven't seen that recording, you should see it, but take it on faith right now that that's going to take order m plus n time, and we are doing this for every edge in the graph. So that means the complexity of this would be order m plus n times m, right? Which is you can say order m square. So that's quite expensive, given that if m could itself be order n square, that means this could be as high as um, if m is order n square, this will be order m to the power 4, right? It's sorry, n to the power 4, right? Put m as n square, that would be order n to the power 4. So quite expensive. This algorithm is known as Fleury's algorithm, and I'm mentioning this just because you'll find it on on online websites, maybe in some of the solutions, but we're not going to implement this because this is a suboptimal algorithm. Although it is an interesting algorithm to design, I sort of redesigned it myself. It's not presented as a decrease and conquer algorithm. That's my own way to look at it when I thought about how I would try to design this. Uh, uh, Basically, you'll just see this presented as an algorithm, but it's really a decrease and conquer algorithm that focuses on just figuring out what the next vertex should be along an Eulerian path, and the next vertex should always be uh, the vertex that you end up with by following a non-bridge edge, as long as there are non-bridge edges out of the current vertex. Only then do you start consuming or burning the bridges. Okay, so any questions on this? So in a directed graph, I guess you could have a version of this on a directed graph where, let's say you're given which vertex to start building the Eulerian cycle from. How do you know which edge uh, is a bridge? Basically, so since bridges are not strictly speaking defined for directed graphs, we would do something like the following. Suppose I am at the source vertex S, and I'm just going to check what vertices I can visit. Right? Maybe I can visit all the remaining vertices. Only then, obviously, will an Eulerian path exist. So what I do is, let's say I have four edges that are coming out of S. These are directed edges. I want to find out which of them is a bridge, which of them is not a bridge. Of course, the word bridge is not strictly speaking defined in the same way for directed graphs. So what I do is, one by one, I try to uh, pretend that I'm going to follow this particular edge, and by following it, by pretending that it's gone from the graph, I then check which vertices would now be reachable from S. Right? If removing that edge does not change which vertices can be reached from S, then I would call that edge as not a bridge. But if removing that edge cuts off my connection to like a bunch of vertices here, then I definitely want to burn this bridge at the end. Having, I first want to visit these regions, and only then will I take that final path which will burn the bridge so that I can't come back here again. Right? So it's the same intuition um, for directed graphs as well, but no need to go into the gory details here, given that it's uh, like an order m square algorithm. What we are really looking for is a linear time algorithm, order m plus n overall.